This is Mr. Joseph with another video lesson, this time covering section 6.4 over dot products. So you should have these notes on your desk and be ready to go. Okay, we'll go ahead and get started here. We've talked about how to, in the previous lesson, about how to add two vectors and about how to multiply a scalar times a vector. But we haven't yet talked about or defined what it means to multiply two vectors together. So say I have two vectors, one vector u, I can have have components u1, u2, and vector v, which I can have with components v1, v2. What would it mean to multiply these two vectors together? There's actually two ways to do this, two different kinds of vector multiplication. And we're going to look at the first kind today, which is called a dot product. And it's named a dot product because we represent the multiplication with a dot. So we say u dot v. And we actually define that. This is in the notes, but we define this as u1 v1 plus u2 v2. Okay, so that's how a dot product is defined. The definition of a dot product we've got right here. So let's see how this works just by doing an example. We're going to look at this one, 45.23. 45.23. Okay, so I've got my, if you want to, you can label these if you want, if it makes it easier for you to see, U1, U2, V1, V2. So we would have, this would equal 4 times 2 plus 5 times 3, which is 8 plus 15, or 23. And maybe the first thing to notice about a dot product is that it is a scalar. We take the dot product of two vectors and the result is a scalar. Okay, so keep that in mind when you're doing a dot product. Your answer should always be a scalar. And you can do these other two examples here on your own. Since it's a video lesson, I'm gonna just allow you to do those exercises by yourself. Here are some interesting properties of dot product. Since we defined sort of a new operation, it's always good to sort of see what sort of properties it has. This, well, we could call a commutative property of dot products. U dot v equals v dot u. Here we've got the 0 vector, which is just the vector with component 0, 0, dot any other vector is going to be the number 0. 3 is sort of like a distributive property for dot products. It distributes over multiplication. Number 4 we're going to look at more in depth here in a second. And 5 tells you how you can deal with scalar multiplication over a dot product. So if you have a scalar outside of a dot product, you can do the scalar times the first vector and then do the dot product, or you can do the scalar times the second vector and then do the dot product, and it'll come out with the same result either way. Or you can do the dot product first and then multiply the scalar. Okay, actually let's look at property number 1 very quickly. So u dot v equals v dot u. Well, we've got u dot v here. What would v dot u equal? Let's just prove this very quickly. V dot u, well, that would be v1, v2 dot u1, u2, which would be v1, pen got stuck here, v1, u1 plus v2, u2. Well, since regular multiplication is commutative, v1, u1 is the same as u1, v1. And v2, u2 is the same as u2, v2. Ooh, v2. Got a malfunction there. It's supposed to be v2. Okay. The point is that this is the same as that. So u dot v is the same as v dot u. So dot products are commutative. Okay. If you go to the next page on the notes, the next page on the notes are asking us to prove the fourth property. Prove that v dot v, a vector's dot product with itself, is the magnitude of the vector squared. So okay. Let me scroll down here just a little bit. Okay. So v dot v, well, this would be v1 v2 dot v1 v2, and according to our definition of a dot product, this would be v1 v1, that's v1 times v1 plus v2 v2, which would equal v1 squared plus v2 squared. Okay, that's the dot product of a vector with itself. And if you remember what the magnitude of a vector is, the magnitude of a vector is the square root of v1 squared plus v2 squared. This is what we looked at in the 6.3 notes. Well, if we take that and square it, right, that'll just be v1 squared plus v2 squared. So these two things are equal. Therefore, the dot product of a vector with itself is the same thing as its magnitude squared, which is something we want to keep in mind. So that's property 5. You can work out some examples here. I'm going to do just example number 1. So we're given 3 vectors. U is -1, 3, V is -4, and W is 1, 2. And we want to find each of the following. I'm just going to do the first example. You can do, well, actually, let's do both of them. Why not? First, we have W times U plus V. Let me get where I can see this. Well, okay. So W, vector W times U plus V. Maybe I want to fill in all the, the vectors in component form first. So W is 1, 2 times U, which is -1, 3, plus vector V, which is 2, -4. Let's go ahead and do this vector addition first. We've got it inside the parentheses. Might as well do it first here. We've got, let's see, this would be -1 plus 2, which is 1, and then 3 plus -4, which is -1. All right, so we've got, yeah, so that's the vector 1, 1, and we're doing, there should really be a dot there. This is W dot that vector. So we're multiplying 2 vectors here. We're doing a dot product. 1, 2 dot 1, -1. This would be 1 times 1 plus 2 times -1, which is 1 minus 2, or -1. Okay, so our result in that case was a scalar, which makes sense because we were adding 2 vectors and then doing a dot product with another vector. There really should be a dot there. The second one, 2 times u dot v. Oh, by the way, if you look at number 1, we did it by first adding the 2 vectors. If you go back to our properties, we had some options. We could have added the 2 vectors first and then did the dot product like we did, or done the dot product of u dot v and then added the dot product of u dot w. So we sort of had, or actually in this case, w dot u plus w dot v. We could have done it that way. Here we've got a scalar times a dot product, 2 times u dot v. I'll take a look at this one. I can see it. 2 times u dot v. So two times -1, 3 dot, that's in parentheses, dot 2 -4. We want to do the dot product first. So u dot v, it would be -1, 2 plus 3 -4, which would be, let me scroll down here, give myself a little more room. This would be -2 minus 12, which would be -14. And we're doing 2 times all that, so we get -28. Okay, so we had a scalar times a dot product of 2 vectors, and our result was a scalar here. Oh, and I guess I should have put, there should be parentheses around this dot product as it was written. One other thing to note as well is if you go up here, if you notice this property, we could have done it just like we did it where we did the dot product first and then multiply the scalar. I could have also multiplied the scalar times either one of the vectors first and then done the dot product. Okay, let's do the next example. Here I've got, given the dot product of u with itself is 5, what is the magnitude of u? Okay, so the dot product of u with itself is 5, and they want to know the magnitude of u. Well, if this was, I was doing this in a live class, this is where I would call on somebody, see if they could figure this out, but since this is a video, I'll just cut to the chase here. You want to use this property. A dot product with itself is the same as the magnitude squared. So the dot product with itself is 5. That's equal to the magnitude squared. Well, if 5 is the magnitude of the vector squared, the magnitude is then the square root of 5. So that's just using that property that the dot product of itself is the magnitude squared. Just sort of demonstrating that we know how to use that. Okay, this will be the end of part 1. Move on to part 2 when you are ready.